see about the design of solid slab in the bridges. Okay, so in the bridges, we're going to design the solid slab. Then we're going to draft the solid slab in the AutoCAD. Okay, so this is the two element we're going to see today: design and drafting of the solid slab of bridges as per IRC loading. Before going into the design and drafting, you should know the difference between the reinforced uh, conventional reinforced cement concrete design with the IRC loading based design. Okay, so you should know the difference. What is the difference? So while you design the elements as a reinforced cement concrete, you follow the guidelines from IS 456 2000 and IS 1026 to 2009. Then design aid SB16 for load calculation. You use IS 875 part 1 to part 5. Based upon the types of loading, you use different type of code books. Okay, so as per the Indian standards. Okay, this is related to the reinforced cement concrete element design. But if you want to design the bridges, okay, you have to follow the IRC loading condition. In case of in the first case, you followed a specific code book called Indian Standards 875 part 1 to 5 code book. But for the bridges, you will follow the IRC loading condition. Okay, then you follow for the analysis purpose, you follow the influence line method. Then the third difference is you will be designing the structure based upon the working stress method in the most of the time. Okay, so this is the three different differences between the conventional design and the design of bridges, that is the design as per the IRC conditions. Okay, so this is the first predominant design. Okay, while the second difference, while you construct any type of structure, whether it may be residential or industrial. Okay, so industrial with the reinforced cement concrete, uh, you follow which method? You follow what is the sequence of your construction? So the sequence of construction, maybe first you will have the shuttering process. Shuttering. After that, you will place the reinforcement. After that, you will pour the concrete. Okay, this is the way you do the construction. After setting of concrete, you will demold that shuttering. Okay, so this is the sequence of work you follow conventionally. But in the bridges, so the design of solid slab will be can be done in two ways. Okay, so if it is a if you going to follow the cast sensitive method, okay, in the site itself, you will cast the solid slab separately. Then you will just lift the solid slab. Considering the weight of the solid slab, you will fix the capacity of the crane. By using the crane, you lift the solid slab and you just place the solid slab. Okay, so mostly the slabs which is there on the bridges, so the slab which is there on the bridges is of simply supported type. So that's why you can either you can cast the slab in the site, and you can place the slab as a simply supported type, or else you can go for the precast construction. So precast construction in the sense, in the closed environment, you will cast the slab. So based upon the pre-stressed method. Okay, pre-stressed method, as a ready-made element you will get it. Okay, so you can transport from the industry, that is from the closed environment to the construction site, and you can just place it as a simply supported element, simply supported slab, and you can proceed the construction in that way also. Okay, so as of now, we have covered the difference from the conventional method of design to the design of bridges and design of solid slab as per the IRC loading. So the next thing is method of design. Okay, method of design also. What are the ways you follow? Okay, so that is the difference we have seen. Okay, so now we're going to see the design of solid slab. Okay, so design of solid slab which is to be used in the bridges. Okay, can you all able to see the screen? Can you all able to see the screen?
Yes, sir.
Yeah. So you're going to see the design of solid slab as per IRC loading. Why you have to design the solid slab as per the IRC loading, so you're going to use that particular solid slab in the bridges. Okay, so that's why you go for the IRC loading. Okay, but before you going into the IRC loading, you should know what you mean by IRC. So IRC is nothing but the Indian Road Congress, which provides the guidelines for the load conditions while you design the elements for the bridges, not only for the bridges, for the transportation. Okay, so in some of the cases the payments also can be designed. Okay, like for example in the airports and all, the runways is there, no, the runways and the payments is there, no, that also can be designed as per the IRC loading. Not only that, highways, national highways and state highways are there, no, so even that kind of uh, payments are designed as per the IRC loading. In shorter form, so what are the structures which is used for the purpose of transportation has to be designed as per the Indian Road Congress recommendation guidelines. Okay, you can use the IS 456 2000. That is the guideline for the plain and reinforced cement concrete. Okay, so that is the difference. Okay, so which element you design, you should consider that aspect also. Which element you're going to design, and what is the method you're going to follow. Okay, so based upon that only your designs will be there. Okay, so this is the first illustration. They are given the design principles of solid slab. Okay, so the design principles of solid slab bridge deck may be illustrated by the following illustrative examples. Okay, so they are given one illustrative example which based upon that conditions only we going to design the structure that we decide to that we desire or that we need. Okay, so first of all, what they are things they are given, what are the things they are given. Design a solid slab. They are asking you to design a solid slab bridge superstructure. The difference between the substructure and the superstructure, right? So what are the things which is there above the ground level, it is called superstructure. What are the elements which is there below the ground level, it is called substructure. Okay, so they are asking you to design a solid slab bridge superstructure having the clear span of 9 meters. So clear span of 9 meters, the length of the bridge is 9 meters. Okay, in that the carriageway of 7.5 meter with 1.5 meter wide footway on either side of a national highway. Like what they are telling, like they are given the span as 9 meters, and carriageway with this the width of the road is 7.5 meter. Okay, so carriageway in the sense that is the way the vehicle is allowed to travel. Okay, so that is the carriageway. That width is 7.5 meter. Then 1.5 meter width is allowed for the footpath on the either side. Okay, so on the either side 1.5 meters is is there. Okay, so the solid slab which you're going to design is for the national highway. So in the national highway there is a bridge located. Okay, so for that particular bridge you're going to design the solid slab. Okay, so then the loading condition what they are given, as per the Indian Road Congress, the loading condition they are given as single lane of IRC class single lane of IRC class 70 hours. So that is the loading condition which has been given. Here comes the influence of the Indian Road Congress. Okay, so as per the Indian Road Congress, the loading condition is given as class 70R, both wheeled and the tracked. So tracked in the sense, if you observe the heavy vehicles and all, there will be two wheels at the same it will be same position. Okay, so two wheel tracks and two lanes of IRC class A, whichever provides maximum effect. Okay, so this is the loading condition which they are given. So based upon the loading condition given, we're going to design the structure. Okay, so before so the textures which is given here, it has to be projected as a rough sketch. Okay, so I'll show the rough sketch now. Okay, can you all able to see the screen? Can you able to see this picture now? Can you able to see the picture?
Yes, sir.
Yeah.
Yes, sir.
So as I told, actually this is the carriageway. So from this point, actually
Yes, sir.
you see the cursor properly. So from this point to this point, it is the carriageway. So only this way is allowed for the vehicle movement. Okay. The width of the carriageway is 7.5. Okay. Then footpath is provided on the both the sides. Okay. So the footpath width is 1.5. So on the one side as well as the 1.5 on the other side. Okay. So in total, it is 9 meters. The width of the decks, solid slab which you're going to design is 9 meters. Okay, so this is the projection. Okay, so the same thing they are given, carriageway and the span. Okay, now we're going to proceed the design. So they are given, so they are given the So they are given the effective span. So the effective span they are given as 9 meters. Okay. Sorry, it is not effective span. It is the actual span, 9 meters. Now, what are the things you're going to design? You're going to calculate. First of all, you should calculate the overall depth. So from the overall depth, you can calculate the effective depth. You know the span. So from the span, you can calculate the effective span also. Okay. If you see here, first of all, we are assuming the depth of the slab. So we are assuming the depth of the slab capital D as 675 mm and clear cover is 30 mm. So altogether it is 675 mm. That is the overall depth. So from the overall depth we are calculating the effective depth. Therefore the effective depth is equal to overall depth. If you subtract the overall depth with the cover, okay, so the 675 is the overall depth D minus cover. What is the value? That is the cover, clear cover, which they going to provide. Okay, minus 30 minus half of the dia. So dia which you're going to use it is that also assumption comes under the assumption part. We're going to use the 26 mm dia bar. So half of the dia bar it is 13 mm. So if you execute this particular calculation, you will get the effective depth as 632 mm. Okay. So similarly, effective span. Okay. So you are calculating the effective span. You know the clear span value. So the clear span is 9 meters plus the effective depth. Also, okay. What is the effective depth? Okay. 632 is the mm is the effective depth. If you are converting mm into meters, that is divided by 1000, you will get 0.63. Then you are adding the clear span, that is 9 meters plus 0.63 meters. You are getting the value of effective span as 9.63 meters. Okay, so this is the way. First of all, you are assuming the overall depth. So from the overall depth you are assuming the from the assumed overall depth you are calculating the effective depth as well as the effective span. Okay, so this thing is over. After that you're going to calculate the dead load. Okay, so I hope you've seen about the reinforced concrete element design. Some of the steps can be repeated or replicated from that. Okay, so there what you will do, you will first calculate the dead load and live load. You'll be doing, so the same thing only you're going to repeat here. Okay, first of all you're going to calculate the dead load. Okay, so what is the dead load per meter run per 1 meter width of the slab is considered. Okay, first of all you calculate the dead load per meter. Okay, so per meter can be you calculate. After that if you multiply by the overall meter you will get the total load. Okay, so that is the idea. So that is the method they follow. Okay, first of all self weight of the dead load 675 is the mm. Okay, what is the dead load of the slab? Okay, so based upon the depth you can calculate the dead load of the slab considering the dimension. Okay, so you know the depth value. So the depth is 675. Then you know the span also. The span is 9 meters and the unit weight. While calculating the dead load, you consider that unit weight always. Okay, by multiplying the dimension into the unit weight, you will get the dead load of the slab first. Okay, so dead load of the slab per meter is 1620 kg per meter. Okay, so the second case is like wearing course. Wearing course is nothing but the floor finishes is applied. So the floor finish is called wearing course. The floor finish is wearing course. Okay, so that particular density is it depends upon the material. If you use the bitumen, what is the density the bitumen has? Okay, based upon that you calculate that particular dead load also. That intensity is 212 kg. Okay, so that is the wearing course dead load intensity. Then you go for the load calculation. Load calculation is in the sense as per the Indian Road Congress, they are given it. They are given it as single lane IRC class 70R. Okay, so based upon that, you calculate the wheel guard load and support of the curb and parapet curb and footway part and rails. Okay, so rails is nothing but handrails is there, no, at the end of the slab the handrails is there, no. So you calculate all the dead loads. Okay, so based upon the which provisions you do, based upon the IRC loading, that is the IRC 70R. You can refer, you can calculate, you can download this IRC recommendation. I also will show, or else it can be showed in your regular calls also. Okay, so the single lane of the IRC load. Okay, based upon that, you take the values and you calculate like this. Okay, so the cumulative addition of this all the load intensity, you will get the total load like this. 1545 kg is the total load due to the total dead load due to the elements which is there on above the solid slab. And this particular load is no, so this is the load intensity due to the self-weight of the solid slab. Okay, so you should know the difference. So the first two case is due to the self-weight of the solid slab, and the case 3, that is the case C, is due to the elements which is above the solid slab. For example, rails. Okay, so I'll show what is the rails and all. Okay, one second. So this is the footpath is there, no. So this element is called rails. Okay, what is the weight of the rail? So they will install the rail directly as a precasted elements. Okay, so that's why the weight is ready made. Okay, so the weight of the one rail is 150 kgs. So we provide the two rails on the both sides. Okay, so two, therefore 2 into 120 into 150 kgs, you will get the 300 kgs. Okay, in total the load which is there due to the elements above the solid slab is 1545 kg. Now what you do, so you're going to calculate the load per width. Okay, so how will you calculate per width? So it is the load per width of the deck. So it is the total divided by the width is 11.03, considering all those things. Okay, so including the carriage weight, including the footpath, and including the width of the rails, the total width is 11.03. So the total width of the slab, the total width of the slab is 11.3. So per width you are calculating as 40 kgs. Okay, so then you are calculating the total load. So the total load is nothing but the load intensity of A plus load intensity of B plus load intensity of C. So you know the load intensity of A, that is 1620. So 1620, then load intensity of B is 212 kgs. Okay, so that is 212 kgs, and the load intensity of C is 140, that you are calculated. Okay, so the overall width, for the overall width we have done it here. So per width only we are doing, no, so that's why 140. So you add all those value, you will get it as 1972 kgs per meter width. Okay, so this is the load which we got. So from the load you can calculate the moment. Okay, so this is the procedure, right? So first you calculate the load as well as you calculate the moment. Okay, so how will you calculate, so the moment generally for the span element having the span, so the moment formula is WL square by 8. Okay, so for the simply supported beam, we use this formula WL square by 8. Since I told, okay, so I already told beam is a simply supported element, that's why we can implement this formula itself, WL square by 8. So we know the value for W. So the now just now we are calculated 9972 is the W value. So you can substitute here. L square is nothing but effective span. So effective span value is what? 9.63 meters. Okay, square divided by 8. Okay, so divided by 8 you will get the dead load moment at the mid span per meter. Okay, so the dead load moment can be at the mid span per meter, that is 22,860 kg per meter is the dead load moment at the mid span per meter. Okay, so so you know the solid span, the solid slab span is 9 meters, actual span, but the effective span is 9.63. But what is the moment at the center or at the mid of the slab? Okay, so that you are calculated. Okay, so the first some portion of the design is somewhat over, like we have calculated the moment. So after that, based upon the moment, we can do the reinforcement calculation also, that we can do at the different stages. Okay, so now we going to calculate the moment due to the live load. Okay, so the moment due to the live load, how can you calculate? So you see the width is lesser than 3 times the effective span. Okay, so like they are given one condition here. Okay, so what they are given, so the span, the width should be lesser than 3 times of the effective span. That is like the width is what, 11.03. It is lesser than 3 into 9.63 is what, 27.89 meter. Okay. So for a single lane of IRC 70R tracked wheel, when placed at the center, will produce the maximum moment. Okay. So there will be a maximum moment at the center. If it is IRC, so IRC is giving the recommendation like that. Okay. So the IRC 70R is giving the recommendation like that. Okay, like at the center of the span only you will get the maximum moment. Okay, why we see, so as I added to that, the two lane of the of class A loading or a single lane of class 70R wheeled vehicle will not produce maximum moment. Okay, so these are all the recommendation as per the uh, IRC 70R tracked vehicles. Okay, like what are the recommendations? Considering the live load intensity will be maximum at the center. Okay, so similarly, similar to the dead load, so the live load intensity also will be maximum at the center. So if you see the dead load, that intensity also is maximum at the center. Okay, so the second, the second recommendation, so the width of the slab should be lesser than 3 times the effective span. Okay, so the width of the slab should be lesser than the 3 times of the effective span. The third recommendation is what? Two lane of the class A loading or a single lane of the 70R loading will not produce the maximum amount. Okay, so these are the three considerations as per this IRC 70R tracked vehicle. Okay, so now we're going to calculate the width as per this recommendations. Okay, by using this expression. Okay, so by using this expression you can calculate the width for live load moment calculation. Okay, so you have the expressions here, you substitute the values. Okay, you have all the values, so that you will get the effective effective width for calculating the live load moment. Okay, so I'll move to the next slide. Okay, so this is the projection of the uh, slab which we intend to design. Okay, so which we intend to design, there is a provision. I shown this to you already. Okay, so carriageway and footpath and handrails on the both the sides. Okay, so this is the depression of the wheel load, how the wheel load is depressed. Okay, if you see, there is a two vehicles moving in the particular bridges. Okay, so how the loads are distributed, if you see at the angle of 45-degree, the loads will be distributed. Okay, so from the CG, from the center of gravity of the vehicle, so at angle of 45-degree, the load distribution will be happening. Okay, so if the two vehicle is moving in the bridge, how it has been distributing the load, you see. Okay, so if we go further, we go for the so we have done it for design moment for as per the dead load. We calculated the dead load moment intensity at the mid span of the slab. Okay, so midspan of the bridges. Okay, similarly, we going to do the load calculation, live load calculation. After completing the live load calculation, we going to design. We going to calculate the moment of the live load. Okay, so that is the thing we're going to see. So dead load calculation is over. Dead load moment calculation is also over. Okay, so after that we're going to go for the live load moment calculation. First they calculate the load 4.57 plus 2 into 0.675 plus 0.085. So what are the values, you know? So this is the value. This is the value of load for the 70R wheeled load. Okay, as per the IRC. Then plus they are considering the overall depth as well as the uh, rail width. Okay, so considering all those things, you get the uh, width like that. Okay, so after that you calculate the intensity. So intensity they are given already as 70 into r. Okay, so 70 into 1000 divided by 9.085 is the span, and 6.09 is the width. Okay, as per the live load calculation, 6.09 is the width. Okay, so at the end you calculate the live load. Okay, so based upon the influence line method, you calculate the intensity of the live load also in the structural analysis subject. Okay, so if you know the values, if you calculated the load, you can calculate the moment, right? Okay, so if you use the influence line method, so to calculate this particular live load amount. Okay, so it is nothing but you know the intensity, so from the intensity you are calculating the moment. Okay, so initially if you consider the dead load moment calculation and all, we directly completed our we are directly done our moment calculation by using the expression WL square by 8. Okay, in case of simply supported beam, but in case of live load, you know, so the dead load, if we consider the why in case of live load, you know, so we go for the influence line method to calculate the moment. Why, you know, like if you see the dead load is constant. Okay, it is the self weight. Okay, so it is constant, it is not going to change, but the live load will change uh, by the span by span. Okay, so if 9 meter is the overall span, so with while crossing the each unit of slab, the intensity is different. Okay, so that's why we calculate, we go for the live load movement live load movement calculation as per the influence line method. Okay, so after that they're going to so this is the carriage. So this all the calculation is there, no? So this is related to the carriage way, carriage way solid slab. Okay, now we're going to see about the footway loading. So footway loading, vehicles will not be allowed to travel, vehicles will not be allowed to move, but only the footpaths. Okay, so only you can walk, you know, so that that loading conditions also we should consider. So from the arc 5.5, that is the from the IRC, they are given some of the recommendation to calculate the load. So from the load, for this the footway path, you can follow the conventional way of calculating the moment. Okay, so here they are calculated the loading intensity, you know, 106 kilonewton per meter. So from the load you can calculate the moment at the midspan. Okay, so load W L square. L square is nothing but the effective span, 9.63 square divided by 8. Then you get the intensity of the movement due to the footway loading at the mid span. Okay, so 224 kg meters. Okay, so now we have calculated the three kinds of moment we have calculated. Okay, so what are the three kinds of moment, you know? Like the first kind of moment is dead load at the mid span. Uh, moment at the midspan due to dead load. Okay, so the first case is moment at the midspan due to the dead load. Okay, so for that, conventionally only you can as per the IRC recommendation, you calculate the load, and conventionally you calculate the moment intensity at the midspan due to dead load. Okay, while for the second case, the live load is calculated as per the IRC recommendation, and the moment is calculated using the influence line method from the structural analysis. Okay, so from the structural analysis methods. Okay, so that is a second kind of method, second kind of moment intensity you are calculated. Okay, so the third kind of moment intensity, so the third kind of moment intensity is footway loading. So footway loading, like so far the dead load moments is due to dead load and live load movement on the carriage wave only we have done. Okay, so the footway moment is also calculated. So the footway moment, how they are calculated as per the IRC recommendation, that is art 5.5 from the IRC only, they calculate the footway moment. So after calculating the load, conventionally the moment is calculated at the midspan due to the footway loading. Now design moment is you add all the moment from the three categories. Okay, due to the dead load, due to the live load, due to the footway load. Okay, so 22,860 is due to the dead load moment. Okay, so the 13,960 is due to the live load moment. Then 1224 moment intensity is due to the footway loading. Okay, so these are all the intensity. So you add all the intensities together. Okay, so in total 38,044 kg meters. Okay, so per meter 38.4 for 38,044 kg meter intensity of moment to be will be applied. Okay, so you are converting, it is in kg meter, so they are converting into kg into newton. For that you have to multiply by 9.8, so you will get the design moment, the final intensity as 3,92,800 Newton meter. Okay, so that is the final moment intensity due to the dead load and due to the live load and due to the footway path load. Okay, so now you're going to design. Okay, so how will you design? Like as I told already, uh, what are the materials you're going to use. Okay, so for particular design of solid slab, you're going to use the M20 grade concrete and HYST bars are proposed to be used in the slab. Therefore, following design parameters are used in determination of depth and reinforcement of the slab. Like for example, in the design of cantilever wall, what we have done. So we have calculated the design parameter before going into the design, like mu divided by bd square. Okay, so you have calculated that design parameter, but you use the design parameter to take the value from the SP16 design aids. Okay, similarly, before going into the design, okay, this is the limit state kind of design. Why? Because you use the modular ratios here. Okay, so you these are all the design parameters which can be helpful for the design loads. Okay, so for you see 6C equal to 6.70 megapascal and 6S equal to 2000 megapascal. Okay, then you calculate the modular ratio 280 divided by sigma c, 280 divided by 3 into 6 6.07, that is the stress due to compression. Okay, so 6.07 you calculate, you substituting, then you are getting the value of modular ratio of 13.93. Okay, so so this is the usual steps. Okay, how you calculate the reinforcement detailing and all. First of all, you go for the neutral factor calculation. Neutral factor calculation is 99.33 divided by 60. So 60 is nothing but the stress 6 or gamma c also. You can say it as in another way. Okay, gamma c. You just 99.33 is a numerical divided by 60 value. It is given in the previous previous slide. Okay, 6.07 and 6s value is 200. Okay, you need the 6s value here. You just substitute this one. So then you get the depth of the neutral axis as 195 mm. After that, you calculate the lever arm distance. Lever arm distance, like, so the expression is there. You require the value of effective depth to get the lever arm distance value. So you just substitute the effective depth value so that you get the lever arm distance. Okay. After that, moment of resistance expression is there. So the moment of expression from the moment of resistance expression, you substitute all the value. Okay, so compression stress value, 6.70 is substituted for the compression stress value. So K value, so the value of K also you calculated from the step 0.138, and D is the only unknown value, and breadth also for 1 meter you can do always, or else you can keep the breadth such. Okay, then 0.894, that is the value of J, lever arm distance, 0.894 D. So you substitute the value. So at the end, the moment of resistance is equal to 0.95 BD square. Okay, so we calculated the effective depth already, but that is based upon the assumption. Now what we going to do, so we're going to check whether the assumed value of effective depth by S is correct or not as per the guidelines. Okay, so that is the thing we're going to see. The moment of resistance value. So the moment of resistance value is what? In the previous step we calculated, no? So this is the total moment of resistance. Okay, 3,72,800. Okay, so you substitute like what you want. You're going to check whether the effective depth which you have provided is correct or not. That is the requirement you have. Okay, so how will you do? The moment of resistance, you keep the D on the one side, you take the other values on the other side. Okay, so how can you do? So D will be on the one side, and moment divided by R into B. So R is nothing but R is nothing but, so this value 0.95 into B. So you substitute the value for the moment, then you will get the effective depth as 626 millimeters. Okay, so this is the effective depth you have. Okay, so from the effective depth, you can calculate the overall depth also. So you 26 is there, no? So you are adding the 30 as a cover and 13 for the half of the dia. So then you are getting the final depth as 632 mm. Hence the depth is same. Okay. So if you see what is the depth we assumed. Okay. So we assume the depth up to 632 only. Okay, 632 mm is the depth we assumed from the initial steps. Okay, so but what is the depth we going to provide? Okay, so we're going to provide the depth. This is the depth to be provided. Okay, 632 only we're going to provide. Okay, but what is the depth is enough. Okay, only 626 is enough, but we are providing 632. Yeah, hence our structure is safe. Okay, so 626 is the depth as per the recommendation, but you are providing 632. So therefore our recommendation is right. We can follow this value for the effective depth itself. So after that we are calculating the main reinforcement detailing. Okay, how will you calculate? Based upon the moment only. So you substitute the moment on the top side, and you substitute the all other values on the bottom side. So, okay, therefore you are getting the area of the main reinforcement as 32 3,299 millimeter square. So from the capital AST, you know how to get the small AST. Okay, first of all, you should assume what is the dia of bar you're going to provide. So from the dia of bar, you can get the spacing for the bars. Okay, so here they're going to provide 25 mm dia bars at 140 mm center to center spacing. Okay, so this is the structural notes which we got at the end of the design. Okay. So after that, we are going for the main reinforcement calculation. So along the transverse direction. So for that, they calculate the moment. The steps are same. So first they calculate the moment. So moment divided by area, you will get the reinforcement. Okay. So for the main reinforcement, they go for that is along the transverse direction. They use 12 mm dia bars at 125 mm center to center spacing. Okay. 120 mm center to center spacing. Okay, so we got all the data, okay, related to like what is the width of the carriageway and what is the width of the carriageway, what is the width of the footpath, and we calculate different intensity also, intensity due to the dead load, and intensity due to the live load, and intensity due to the footway loading also we are calculated. Based upon the load intensity, we ensure uh, whether the depth of the slab which we assumed initially is correct or not. Okay, so if your assumption is right, you can go with your assumption itself. Okay, you can go with your assumption itself. So that we have ensured. After ensuring that, we calculated the we done the reinforcement calculation based upon the moment along the longitudinal cross section as well as along the transverse direction. In one direction, we got the structure laid as we going to provide 25 mm dia bars at 140 mm spacing. In the other direction, we're going to provide 12 mm dia bars at I'll see 12 mm dia bars at 125 mm spacing. Okay, so this is the kind of dia of the reinforcement you're going to use, and this is the spacing, center to center spacing you're going to follow in your particular design. Okay, so within this we are completing the design of solid slab. Okay, so solid slab for the bridges. Now further we're going to do the structural detailing of the solid slab which we are designed um, by using the design aids we have. We're going to draft whatever the things we have it in a text form, right? Okay, so from the text point we're going to draft the detailing, structural detailing in the AutoCAD in the further, okay, in the further sessions to be seen. Okay,